Hi everyone, here's our second session. Today we are going to talk about the Samsung phone, especially in the Exynos chipset, which is delivered by the Samsung. In this talk, we will tell the story on bug hunting on the Exynos Coprocessor and the experience we deal with the sensor bug bounty. Hi, I'm Billy. I'm from Starlab, do research on the news and kernel. As a speaker of Hikang, DevCon, OP1, POC, and CoBlue.
Hi everyone. Hi everyone. It's me again. I'm Peter from Starlabs. I do research on iOS and Android platform, and I have shared my past research on POC, ZeroCon, OffensiveCon, and other conferences before.
Hello everyone, I'm Ramdhan from Starlabs. I'm mainly doing research on Linux kernel and Android. I've shared my research on conference like DevCon and HitCon.
Here is our agenda. First, we will talk about the whole slide background, and we will show the bug we found, root cause and its patch, and we will choose two of them for exploit. Explain the path to get root from the untrusted app, and go to the final conclusion. Since we do the research on the Android kernel, it has many mitigation and security protection. As I said in the previous content, it has PAN, PSN, UAO, CFI, PAC, MTE, KSLR. Android also enables many kernel configure for security, such as init on stack, init on heap, the debug list. And Samsung has its own mitigation like kernel DFS and physical ASLR. So we talk about the Android exploit. We like to classify the attack service to universal chipset vendor and module exploit. Universal exploit uses the vulnerability that can affect on almost any Android phone because the vulnerability is under the more core part of the Android ecosystem. For example, Linux kernel unit socket, TCP UDP socket, binary. Those are the most core IPC under the Android. When we talk about the chipset, it means that a attack service is from a specific chipset. For example, Marine GPU and Qualcomm GPU. It won't just affect a single phone, but it will affect all the devices use this GPU. Vendor also has its own sleeper driver. Exploit then will be the vendor exploit. For example, Samsung NPU. The affect score will be very limited, usually under the branch module. Each mobile phone has its own unique attack service, like we Pixel GSP. Therefore, the attack service we are going to show today is under the vendor specific, which is the Samsung Exynos NPU. In a Samsung Exynos phone, it has a attack service like Exynos NPU. Some Exynos phone use the Marine GPU. Some Exynos phone use the Escape GPU, and also has some Exynos baseband. Why we choose Samsung Exynos? Samsung tried to build its own SoC, and SoC now while used in Europe, Middle Eastern, India, and part of Asia. In 2022, Escape GPU also in the Exynos to replace the Marine GPU. It means there will be more driver code come to the phone. Exynos NPU and Escape GPU both can access from the application. Untrusted app can IO control and open the vendor NPU device and the GPU device. Also, there's a few Exynos bugs or exploit in the past. NPU GPU Exynos policy made it perfect target for LPE, and Samsung is adding new code to its own SoC. After 1 month research, we found out the 13 bugs in the Exynos, 10 of which is belong to the Exynos NPU, and we will analyze them in the next part. Each driver we first will looking into the unlock IO control, which is the vertex IO control, reachable from when IO control on the device vertex 10. By open the driver, it will allocate a new session for us, and we will set a session v context, which is NPU vertex content, to our file playback data. The copy is from the region open to the NPU vertex open. File's previous data is structured NPU vertex context. It contains the state, ID, log, queue, and the vertex. There are 6 state contexts can be. It changed by reach the specific sequential of the I/O control. Also, some I/O control requires the content to be in a certain state. Also, for the NPU queue, it contains the input-output buffer for interact with the NPU. Which some background information, we will start show the vulnerability we found to you. First is CB25 23095. It is a double-free vulnerability. In function prepare IMB info. IMB info was allocated and assigned to the session first. If the session IMB size is quite big, we'll go to p-error and free the IMB info, but it didn't clean the pointer in the session. This IMB info can be free in another function called undo as graph each state. It fetches the free IMB info from the session and free it again to cause double free. Samsung fixed it by not free the IMB info in the p-error call path, so it won't be free again in another function. Second vulnerability is CB2025 23097, which is outbound write. The bug is under the function vertex I/O control. The NPU profile area will be updated for every I/O control. The type index is user space path combined with an operation with the hash FF. Range will be from 0 to 2055. But this NPU profile array only can contain 20 items, and the NPU profile array is inside the NPU vertex content, which is within the object NPU session. If we pass the bigger command, it will cause outbound access on the NPU session. And below is the GOPS. We can override this function pointer to control the kernel PC for the exploit. Samsung fixed it by trade the type before access the NPU profile, so no out-of-bound access to the NPU profile anymore. The third bug is the CPE2025 23098, another double-free vulnerability. In the function VB unmapping DMA buffer, buffer's DMA buffer is not clear after the unmapping. Function NPU vertex unprepared and function NPU vertex flush both can reach the VB unmapping DMA buffer, but they will use the different lock. NPU vertex unprepared use the vertex lock, while the NPU vertex flush use the vertex vcontext vertex lock. It means that two functions can be reached at the same time and put all the same DMA buffer to cause double free. Samsung fixed it by null it after the DMA buffer pull immediately, so it will reduce the chance to get double free. The fourth is the CBE2025 23099, which is outbound access to in the function NPU queue allocate. It will allocate based on the C count if the NPU queue state allocate is not set. In other words, if NPU queue state allocate is set, it will return success. In function NPU queue prepare, NPU queue state allocate will set. If we call NPU queue allocate, first it will allocate object with a smaller C count and set NPU queue state allocate. Then call NPU queue allocate and a second time with the larger C count. It will not reallocate again, so the process will handle user data with the larger C count and cause outbound access under the old allocate object. Samsung patch by return error valid in the NPU queue allocate, so it won't process the user data second time. Next, I will hand to Peter for the rest bar analyze and exploit technique.
Okay, here we will start to talk about CB 2025-23100. Actually, this CB contains two flaws. For NPU session object, the content of the out fence FD array was first initialized to -1. And then in this function NPU session queue, which is shown in the screenshot, it will create a new NPU SYNC file object if it has not been initialized yet. You can see it check if it's -1. It will also allocate a new file descriptor and store in the NPU session. But after the FD install function, user can close this file descriptor and create a new file object with a different file time, but the same file descriptor number. So later in another branch, you will call this function NPU SYNC update outfence with the previously created and stored FD in the session point outfence FD. And then in NPU DMA fence to SYNC PT, it did not check if the fence pointer is fetched by the NPU SYNC file get fence is valid or not, which will cause a non-pointer dereference and crash. And the second issue is also a DOS bug. Maybe it's the reason why Samsung merged the two issues into one. And this DOS is from the NPU firmware side, and it's found by the random test. Samsung NPU will need to call this VS4L Vertex IOC bootup init IO control before calling other features. And if we call this IO control with different types, the NPU firmware will trigger a watchdog timer reset and make the application processor, which is the CPU, also crash. And for this one, we didn't dive into the root cause of it. And next, CB 2025-23101 is an arbitrary kernel-free bug, which is quite strong. In kernel VS4L profile node child, there's a child array contains address from user space named UP. And in the loop, copying from user VS4L will copy data from user to the kernel address called KP and assign the variable temp KP in function VS4L profile node child. And it then updates the child array to the temp KP variable as shown in the left picture, the last line. The problem is it only processes 2 items in the loop, but the array actually have 3 items. So the last item in the child array, which is child array index 2, will left with the user controlled address. When the last item in the child array can be controlled with any address, it will finally reach function free VS4L profile node to free all the 3 items in the KN point child. KN point child here is the KP point node point child assigned in the function shown before. You can see the last line here. The child will be assigned to the KP point node point child. And this will give us an arbitrary primitive, and it's quite strong for exploit. And the patch is also simple. And Samsung processed all the items in the array instead left one, the last one. So I think the part is probably introduced due to the bad internal code review. Next is CB 2025-23102. It's a double free bug in function VBQStop. This function will free the Q point formats without clearing the pointer. And this VBQStop K-free can be reached by VS4L Vertex IOC stream of IO control. We can trigger the double free easily by calling VS4L Vertex IOC stream on and VS4L Vertex IOC stream off IO control pair in sequence twice. The patch is also simple. It's just set num to the Q point format or formats after freeing it. And till now, we can see that the Samsung Exynos NPU have introduced a lot of this kind of double free bugs without clearing the pointer. Next one is the out-of-bound access in function NPU Q update assigned with CB25-23103. The variable C here is a user-provided container list, and this function will use C point count to process a loop without checking if it's larger than the actual Q list point count. During the loop, it takes Q container that could come out of bounds, and even it assigned Q container count without any check. Then out of bounds or even arbitrary write could happen if we have a proper heap layout. To patch this bug, Samsung checked the count for user-provided container lists before start processing containers in the loop. If there's mismatch between QList count and C point count, it will just bail out and return error invalid. Next one is CB2025-23107, also the last bug we found in Samsung NPU. It's also an out-of-bound bug and similar to the previous shared one. In function, but in a different function subroutine. In function we fill VS4L buffer, it didn't check if user-provided array of buffer in container is smaller than the actual size of buffer in QList or not. Then in the loop, it fetched container from QList point containers and get variable k from the QList point containers I point count. And here C is the user provided buffer, and use the QList point count and k, which is the QList point containers I point count, to iterate C to assign values. If C point count is smaller than QList point count, or C point containers I point count is smaller than k, then it will lead to arbitrary read or out-of-bound read primitive with the proper heap layout. And the patch is the same as previous one. They will check C point count before the loop. And these two bugs are in different functions routines, so Samsung assigned with different CVs for them. After discussing around 10 different bugs in Samsung Exynos NPU today, we'll do a brief summary. So Samsung Exynos has different models. Not all bugs can work on different models of Exynos. Some of the bugs, they only exist on specific model of Exynos, such as CB25-23101. It only exists on Exynos 1380. And some of them exist on both higher end and lower end models, such as CB2025-23099 for Exynos 1480 and 2400. Most of the bugs are exploitable, so we will pick two interesting one next as an example. Next, we will talk about how to exploit these NPU bugs on modern Samsung devices and bypass the mitigations. In case you don't remember this one after 10 bug details, let's do a simple recap first. The first exploit we share is CB2025-23101. It's an arbitrary free bug in the get VS4L profile node child. By providing the kernel pointer as last item of child array, VS4L vertex IOC profile on IO control will free the kernel pointer. Since all modern mobile phones have the kernel ASR as well as the kernel heap randomization, and we are wondering, can we spray a lot memory and have a fixed address that always has our targeted kernel object? And the answer is yes on Android. By repeatedly rebooting and collect kernel object address, we are able to find a likely address. And thanks Magisk to make this step much easier than expected. But this address could be model, version, and memory independent. The memory here means how many RAM has left in this phone. For smaller versions like a 1 or 2 month gap, it could be the same, but also depends. In the end, we choose socket buffer as the candidate to free. We will reclaim it as a PyBuffer object, which is quite often Android exploit text. Since during our test, this kernel object is easier to predict and not make phone out of memory and reboot. Also, this object is easy to reclaim as PyBuffer. So here's our step. We first spray the socket buffers, and we call the arbitrary free I/O control in NPU to free the socket buffer. Then we reclaim the socket buffer as PyBuffer, because we can read from the socket buffer back to get the pipe OPS to confirm that our socket buffer get reused. And then we use the leaked pipe buffer OPS to bypass KSR and get AC Linux state address. Then we spray the socket buffer again with the AC Linux state address. Then we could write the pipe buffer with value 0 to disable the AC Linux. This is because Samsung Exynos do not have AC Linux developer disabled, and AC Linux state also not protected by the Knos EL2 hypervisor. And what left is a standard operation. We just repeat the previous steps and overwrite the shell library and hijack init process to pop up the reverse shell. Besides socket buffer, we can also choose page tables. From our spraying test, this one can also be semi-predicted. So we first spray a lot of page table entries, and we call arbitrary free I/O control to free the page table pages. And then we reclaim as AIO pages since they are the same order and same migrate type. Then we could rewrite the page table entries directly from user space address instead of like spraying in socket buffer again and again. Since Samsung Exynos do not have physical memory slide, we could override the SNA state by the linear map address. Then we just do the same steps as before. Next, I will hand to my colleague Ramdhan to share exploit for another bug and do the final summary here.
Hello everyone. So now let's talk about the exploit for the second bug that we found. So this is the CVE 2025-23099, which is out of bounds access in NPU. But before that, I'm gonna explain some background about how NPU use the input queue and the output queue in driver interaction. In NPU drivers, we can allocate input queue and output queue for communication. Now we can see in the structure, there's a fixed amount of item in array that we can store queue. In queue is there for the input queue and out queue is for the output queue. Now each have NPU max queue amount. And we also can see the NPU vertex context structure contain the NPU queue, which also contain our input and output queue. We can allocate input or output queue via IOCTL, and we can choose any index of queue array where our new queue allocated to. And it will allocate via NPU queue prepare function, and then it goes to NPU queue alloc. Then NPU alloc queue function let us to alloc a queue. There's a queue list variable, and it's our new allocated queue. And inside the queue, we can alloc certain numbers of containers. And inside containers, we can allocate certain numbers of buffer. Before we want to allocate a queue, there's a check if queue list is already allocated before. By checking the NPU queue state alloc, if this flag is set, the driver don't want to allocate containers and buffers in this queue again. If you see this clearly, this if condition will just return 0. So if there's a input queue or output queue is already allocated before, then the NPU queue alloc function just return 0. And it proceeds to do another thing with already allocated queue. And then it continue to call NPU queue mapping function. And in NPU queue mapping function, it will assign you allocated containers count to their count variable. So if there's a allocated queue with certain numbers of containers, then we call this function again. This means this function can override count with larger number than previously allocated container. Then they also do the same thing for every buffer on each container. They just override the count from previously allocated buffer inside the container. That means we have malform number of containers inside the queue, and inside container we have each buffer also have malform count. That means it's larger than the actual object allocated. And this will lead us to controllable state to perform exploitation. Next, we search any function that can be used to perform exploitation. The first one is in fill vs4l buffer. We can reach this function using ioctl qbuff bundle cancel. And as you can see, if we have number of buffer is larger than the actual object, we can read past the bounds of the buffer. And we can use this out of bounds read to leak some data past the buffer. Second primitive is if the number container is larger than the actual object, it means we can make container object located at pass out of bounds. And if we can control the out of bounds data, it means we can control buffer's pointer to perform arbitrary read. And there's a third primitive is heap out of bound 4-byte write. It's the condition where we have number of buffers in container is larger than the actual object. So if the queue buffer is located past out of bounds, we can perform out of bounds 4-byte controlled value via buffer arrow_i.offset. But it's also have a limitation where it's limited in 4-byte write, and the offset also it really cannot control. Now let's talk about how this exploit visualize. First, we need shape a heap such we have our buffer object adjacent to victim container. Now let's say we shape the heap object and we allocated buffers and victim containers in kmalloc 1K. Then using 4-byte out of bounds write primitive, we can override the container's buffer's pointer. But like I said before, this out of bounds write is limited in terms of size and offset. And we can only write the first byte of pointer. And what we do is we do another heap spray on kmalloc 512. So we have victim buffers adjacent to the second victim containers. And actually the victim's containers buffers pointer is point to the to victim buffers at kmalloc 512. And we first using out of bounds read, we read the buffers pointer on the first victim container, which is the victim buffer's address. Then after we get the value, which is the victim buffer's address, we increase the values, and so it's point to the second victim containers. We do this using out of bounds write. So after the buffers pointers point to the second victim containers, we can using the first auto bound write to add 4 to the buffer pointer, so we can overwrite higher byte on second victim container. So that means we can control full 8 bytes on the on the buffer's pointer on second victim container. Then by using the same path as before, we can achieve arbitrary kernel read-write on the second victim container. Then after we get kernel arbitrary read-writes, there's many things we can do, like pointed my colleagues before. We can disable SL Linux and achieve root shell by traversing the kernel test and find the libc file. We can overwrite libc to hijack init process and do like loading kernel module or giving us the reverse root shell. Next, we jump to the conclusion. First is USOC and driver are always come with new bugs. And second is mitigation is aligned with all models to take effect. Last thing is fragmented source management is more vulnerable. Now I gonna tell about the timelines on how we report the bugs. First, we found the bugs and exploit at late 2024. When we writing the exploit, we intended to submit as ISVP, which stands for Important Scenario Vulnerability Program. This program said any working exploit on Samsung S series, it will get higher reward. And you can check it at Samsung website. But turns out, claim that all these bugs are not eligible for ISVP. For your information, we submit 4 LPE exploit from 4 different bugs that work on Samsung S24. And they said the Exynos are not eligible because it handled by different company. And Samsung cannot handle this bug. And in the end, Samsung reward are for 1 until 3K for each report. And it finally fixed all our bugs, 13 bugs at June 2024. And these are the reference that we use in this research. And above is what we share today. If you have any question, we are here after the talk. You can approach to us for any question about the slide. Thanks for listening.
ありがとうございました。Thank you for your presentation. And we have Q&A time. If you have a question, please raise your hand. We have received a question online. The question is this a problem specific to the NPU? Are there any characteristics that are different from general implementation flows?
Yes, all these bugs are from Samsung Exynos NPU. They do not affect the Linux mainstream or other drivers.
So I was curious if you can talk a little bit about your methodology for finding the bugs. Is it fuzzing? Is it manual static analysis combination? Yes, thank you.
We find all the bugs by code audit, not like we do some basic fuzzing, but yeah, we just found some dumb bugs like DOS, sort of that.
Thanks for sharing your research. So you identified a whole bunch of bugs, 11 or 10, I don't know. But is there any mitigation or combination of mitigation that could prevent these from being exploitable? Or is it like so many bugs that there's no way to be mitigated with what we have now, I guess?
You can use MT to mitigate them all. Like if you have MT, none of the bugs will be exploitable. Unless the arbitrary free one, I guess. And other out-of-bound guests, I think they will be all caught by MT. But the problem for MT is that they only shipped with the Pixel series. So on Samsung, there's no such a mitigation. And I think they only add mitigations on the post-exploit part, like the defects to stop you from getting the root shell. But I think that one is not very hard to bypass. And yeah.
Okay, so just quick follow-up on the MTE. So MTE, as you know, is kind of deterministic, or is it probabilistic? So if you do it a bunch of times, you might hit the actual tag right. So would that make your job harder, or just exploit will take more time if MTE was on?
So MT will stop the bug from the triggering stage. So once the bug is triggering, before it gets any other primitives like arbitrary kernel or rewrite, it will already bail out. So yes, it do makes the job harder. And yeah, you probably need very good bugs to bypass it. Like our last talk, yeah, if it's right on read-only files, because Android do not have runtime the signature check, and also if it's page user free, the MTE also cannot stop it. So basically, you need very good bug. Yeah. Yes.
Thank you.